Welcome SKM Tahap 3 students to this explainer. Today we're taking a highly focused professional dive into the absolute backbone of modern industrial automation, and that's pneumatic systems. Look, whether you're aiming for a career in advanced manufacturing, robotics, or facility maintenance, mastering this stuff, it's absolutely essential for your vocational toolkit. So let's get into it.
Here's our game plan for this session. We'll kick things off with the basics of pneumatic systems, map out the main components, and then we're going to analyze both single-acting and double-acting cylinders. Finally, we'll wrap up with some practical maintenance strategies and system advantages.
All right, part one. Let's establish what a pneumatic system actually is at its core. To really build a solid academic foundation here, it helps to look at where the word itself comes from. Pneumatics is actually derived from two classical Greek words. You've got pneuma, which means air or wind, and matic, which signifies movement. Put them together, and you literally have the control of movement using air. In an industrial context, this means we're utilizing highly compressed air to securely transmit energy, create motion, and perform some pretty heavy mechanical work in an automated setting. Now, you might be wondering, why use air instead of oil? Well, when we compare pneumatics to hydraulics, a really clear distinction emerges. Hydraulics use liquid or oil, which, don't get me wrong, is great for extremely heavy lifting. But it comes with the constant risk of messy fluid leaks. Pneumatics, on the other hand, use compressed air. This makes them exceptionally clean and capable of incredibly fast response times. And that is exactly why pneumatic systems are the gold standard for industries that demand high purification and zero contamination. Think food processing, printing, and textiles.
Moving right along to Section 2, let's see how this all builds into a complete structural network on a macro level.
Every pneumatic setup operates on a strict hardware hierarchy. It maps out exactly how a signal and energy flow from start to finish. At level 1, you have your energy supply, which is where the compressed air is generated. Moving up to level 2, we find the input elements, basically your sensors, which detect conditions and send signals. Level 3 contains the processing elements, like specialized valves, which take that information and decide where the air needs to go. And finally, at level 4, we have the actuating devices. These are your outputs, the physical cylinders and motors that actually get the mechanical work done.
Understanding this flow as a system block diagram is just a critical visual roadmap for any technician. It perfectly demonstrates the logical path of how raw energy at the very bottom is carefully controlled, sensed, and processed until it becomes a highly precise mechanical output at the top. Honestly, grasping this flow is your key to diagnosing system faults down the line.
Down at that base level of the hierarchy is a vital piece of machinery, the air compressor. You can really think of the compressor as the heart of the entire operation. Just as a human heart pumps blood, the compressor converts mechanical energy, usually from a motor, into the pressurized, compressed air needed to drive every single downstream component in the network. Without a healthy compressor, the whole system just flatlines.
Let's zoom in on the top of our hierarchy now, the actuating devices, and analyze our first major mechanical component, the single-acting cylinder, or SAC. The structural design of a single-acting cylinder is wonderfully simple but highly effective. It has just one inlet for the air to enter on one side and a coiled mechanical spring on the other side of the piston. And it's that spring that defines exactly how this specific cylinder operates.
So, the crucial takeaway here is that in an SAC, the compressed air only does the mechanical work in one single direction. The air enters that single pressure port and forces the piston out. But how does it get back? That's where the internal spring kicks in. Once the air pressure drops, the spring forcibly retracts the piston right back to its starting position. Because it relies on this spring, the return stroke is incredibly fast. However, it really cannot carry a heavy load on the way back. As SKM Tahap 3 technicians, you are going to encounter SACs all over the factory floor. Because they provide strong force in one direction and a super fast, unburdened return, they are universally used for things like clamping workpieces securely in place, running automated cutting machines, stamping or pressing operations, and your basic lifting tasks.
All right, Section 4. We need to contrast the SAC with its more flexible, heavy-duty counterpart, the double-acting cylinder, or DAC. The fundamental mechanical difference between these two is all about how that piston returns. While the SAC relies on a mechanical spring and has only one air port, the
The DAC features 2 distinct pressure ports and completely eliminates the internal spring. Instead, a DAC uses alternating compressed air to power both the extension and the retraction of the piston. This is a game changer because it gives you active, controllable pneumatic power in both directions. What's really fascinating about this mechanism is how precise this active alternating power can be. When pressurized air enters the rear port, it pushes the piston rod out, but then a valve actively switches the airflow. Pressurized air suddenly enters the front port instead, actively forcing the piston back in while exhausting the old air. This grants you total pneumatic control over every single millimeter of the stroke.
Because a double-acting cylinder delivers sustained, controlled force in both directions, it is the absolute go-to choice for complex automation. You'll install DACs in robotic arms, in systems designed for carrying heavy loads back and forth, advanced contactless sensing setups, and even safety mechanisms meant to suddenly stop heavy loads right in their tracks.
Finally, let's transition from academic theory directly into the practical, hands-on skills you actually need: maintenance and system evaluation.
A pneumatic system is really only as good as its maintenance schedule. First rule, you must limit the input pressure to a maximum of 6 kilopascals. Anything higher, you're going to quickly crack those internal rubber seals. Second, for lubrication, always utilize a double glass filter filled specifically with SAE10 oil. This automatically introduces micro droplets of oil into the air to keep the seals perfectly healthy. And finally, and I cannot stress this enough, you must regularly drain the condensed water from the compressor tank. Trapped water turns into moisture in the lines, which makes seals stiff and prone to cracking. Seriously, it is the #1 cause of cylinder leaks.
When properly maintained, these systems are just incredible. Industries invest heavily in pneumatic automation because it is exceptionally fast. We're talking response times in literal milliseconds. It's inherently safe and environmentally friendly since there's zero risk of toxic oil spills. Furthermore, the components are surprisingly cost-effective and they are highly shockproof, making them durable enough to survive the absolute harshest manufacturing environments without skipping a beat.
So, you now understand the theory, the hierarchy, the mechanical components, and the vital maintenance required to keep it all running smoothly. Considering the incredible speed, safety, and cleanliness of compressed air, my final question to you is this: what real-world industrial automation problem will you solve next using pneumatic systems? Take this foundational knowledge, apply it creatively to your upcoming practical workshop exams, and keep innovating out there.